Hello friends, in previous session I have discussed uniform continuity. In this session we'll take some results about the extension function, then we'll study extension theorem and one result related with continuous function. So our first theorem is that let xd and y row be metric spaces, and f from x to y metric spaces and a be subset of x. If f from x to y is continuous function, then f from ad to or f restricted to a from ad to y row is continuous function. So we'll prove this result by using fundamental theorem of continuity. So let G be open subset of Y. Now since f from x to y is continuous function, therefore inverse image of open set is open. Therefore f inverse G is open subset of x, and therefore f inverse G intersection A is open subset in AD. Now f restricted to A inverse G is same as f inverse G intersection A. Implies f restricted to A, its inverse G is open in A whenever G is open in Y. And therefore by sufficient condition for continuous function f restricted to A from A to Y is continuous function. Note that if f from A to Y is continuous, then f from x to y may not be continuous. Okay, note. If xd and y row are continuous are metric spaces, A subset of x and f from A to y is continuous function, then f from x to y may not be continuous function. Justification. We know Dirichlet function fx is equal to f from RU to RU defined as fx is equal to 1 if x belongs to Q and 0 if x belongs to Q complement. This function is discontinuous at every point at each x belongs to R. We have verified it by sequential continuity, or by using epsilon delta also you can easily verify. Now to check f from Qu to Ru is continuous. If I take this function, here for this plate, let G be open subset of Ru. Case 1, if G contain 1, then F inverse G is equal to Q is open in Q. And case 2, if G doesn't contain 1, then F inverse G is equal to phi. Okay, actually F restricted to Q, F restricted to Q, right? F restricted to F inverse restricted to Q is equal to phi is open in Q. Thus F restricted to Q its inverse G is open in Q for any open subset G of Ru, and therefore F restricted to Q from Q to Ru is continuous function. So this function is discontinuous at each point and it is continuous at from Q to Ru is continuous function. Okay, so from A and B we have verified result. Okay, A and B gives a required example, right? Now, if I we'll take extension theorem without proof. Extension theorem. Without proof. So what is the statement? Let XD and YRO be matrix spaces. Let XD, YRO be matrix spaces and A be dense subset of X and A be dense subset of x, subset of x. If f from a to I is continuous, if f from a to I is continuous function, then there exists unique continuous function g from x to y such that g restricted to a is equal to f if and only if limit f of y belongs to a and y tends to x, exist in y. So this is your extension theorem. In general, result is not true. Now we'll take one lemma. So let xd and y row be metric spaces. Let xd y row be metric spaces and fg from x to y are continuous functions. We have two continuous functions from x to y. Then set of those x, then set A is equal to set of x belongs to x such that fx is equal to gx is closed in x. So for this, it is sufficient to show that a complement is open in x. For this, it is sufficient to show a complement is equal to set of x belongs to x such that fx not equal to gx is open in x. Then we are through. So let a belongs to a complement. Then fa is not equal to ga, and therefore d of fa ga is equal to some distance is greater than 0, 1. It is greater than 0. Now since f and g are continuous, since fg from x to y are continuous functions, therefore fg are continuous at a belongs to x. As these are continuous function, therefore for given epsilon greater than 0, there exists delta greater than 0 such that d of x less than delta implies rho of fx fa less than epsilon and rho of gx ga is less than epsilon. Right? So now 0 less than eta is equal to, here rho of Okay. Now rho of FAGA by triangle inequality, this is less equal rho of FAFX plus rho of FXGX plus rho of GXG. But now this is less than epsilon plus rho of FXFAGX plus epsilon whenever d of x is less than delta by 2. And therefore, for epsilon is equal to 2 eta by 3 greater than 0, 2 eta greater than greater than 0, eta minus 2 eta by 3, this is 2 epsilon, eta by 3, sorry, is equal to eta by 3 is less than rho of fx gx, right? By taking epsilon is equal to eta by 3, there is again some delta. There is again some delta depending on that eta, So we are getting this one. Is it right? So for epsilon is equal to eta by 3, we are getting this one. Okay. For given epsilon greater than 0, this is your d epsilon, right? Delta greater than 0. So this implies your x belongs to rho of fx gx is greater than 0, that is fx is not equal to gx whenever d of x is less than delta, implies x belongs to A. For any x belongs to S delta A, x belongs to S delta A, is it right? And therefore S delta A is contained in A. Okay. Thus for A belongs to A complement. A is arbitrary. Since A belongs to A complement is arbitrary, thus for arbitrary A belongs to A complement, there exists delta greater than 0 such that S delta A is contained in A complement, implies A complement is open, and therefore A is closed set. A is closed set. Is it clear? So with this discussion, today we'll stop our session here. Thanks for listening session carefully. Bye bye.